Good afternoon, everyone. My name is Guang Sin Lu. I'm a PhD student from the University of Southern California. So today I'm going to introduce my research, Spatial Microbial Community Structure in a Shallow Sea Hydrothermal System. I think in previous talk, they already talked about a lot early life and extremophile, why we need to focus on the hydrothermal system. So I don't want to keep repeating it. So the question I want to ask in my research is I want to figure out the interaction and linkage between the microorganism and the geochemical cycle in a high temperature system. So there are three different types of hydrothermal system, like the terrestrial hydrothermal system. The most famous example is the Yellowstone National Park, and the deep sea hydrothermal systems such as the Black Smoker or Lost City. Both of them were investigated a lot, like in previous talk, but I focus on the shallow sea hydrothermal system. Shallow sea hydrothermal systems are geochemical and physical transition between the other two systems. It's more complicated than the other two systems, and it's very interesting. But however, not too much research come here. So the shallow sea hydrothermal system is just like a golden mine to open up. So my sampling site located at the Milos Island, Greece. It's on the South Agency, and the Saganaki vent is 300 meters offshore of the Paleochloride Bay, and the water depth is around 12 meters. And this is the first difficulty I met when I started this project because I don't know how to swim. And we need to do scuba diving to collect sample. So my advisor, young man, he helped me to collect all the sample in last summer. Yeah. So, and this is my sampling site. So the white mat cover on the vent. So and they're 2 meters away from the central vent. There are some seagrass cover on the sediment. And between the seagrass area and the white mat area, there's a transition zone. So we collect the 4 sediment core. It's around 20 centimeters in 4 different places. And plus the background area is like around 80 meters away from this vent. And we also collect some surface sediment, pore fluid, venting fluid, and the biofilm. So this is how we collect the sediment coal under the water. And we bring this sediment coal to a board and use a rhizome. And every 2 centimeters, we drill in a hole and put the rhizome inside and collect all the pore fluid. And those pore fluid sample we use for the geochemical data analysis. And the temperature and the pH were measured in the field. So this is a transect of the sampling site, like here. So this part, this is most close to the vent source. So the temperature is around 80 degrees Celsius and decrease to 20 degrees Celsius during like 20 centimeters times 2 meter scale. And the pH increased from 4 to 8. Okay. And so at first I predict if the venting fluid and the seawater only mix to each other, the profile, the pattern gradient should be correct with both depth and the distance. But when I take a look at my geochemical data, so like the sulfate, manganese, and the total dissolved nitrogen, they only function with the distance. And the dissolved organic carbon correlate with the depth. And the iron or arsenic, they are more complicated. So I cannot see any very clear pattern associated with just distance or depth. So it might be some other thing that regulates the geochemical cycle here. So microorganism will be the only answer in this environment. So I choose 16 samples and sent for parasequencing. So it includes 3 samples from each sediment core, from top, middle, and the bottom, and the venting fluid from white mat and the pore fluid from transition zone, and the surface seawater and the field negative control. So this is a preliminary data I just got like around a month ago. So I got like around 1.5 million sequences, and let's take a look at this column. So the 4 column is from the 4 different sediment core, and the seagrass and background core, they looks very similar. The microbial community just switch with the depth. So that's zoned in these 3 previous sediment core, and take a look at the white mat first. Okay. So the deepest sample is most close to the vent source. It dominates with archaea. It's like roughly 70% archaea in whole sample. And it dominates with some mesonotroph or some hypothermal file. And it switched to aquificate. And because those archaea, they produce a lot of hydrogen. And those aquificate, they can use hydrogen as the energy source. And with the depth decrease, whole community switch to the actinobacteria and the firmicutes, those mesophile, and they can adapt in the anaxic and the axic environment. And the next part is the, let's take you the blue part. It's a proteobacteria. So the proteobacteria is dominant in all the sample except for the vent sample. And they dominate with the epsilon and the delta. And this is the community switch that cause the regular sulfate cycle in this area. So the epsilon proteobacteria, they are famous sulfur oxidizer, and they can produce sulfate. And the delta proteobacteria, they use sulfate a lot. They are very famous anaerobic sulfate-reducing bacteria. So based on my geochemical profile and my community profile, close to a vent, it's not only the venting dilute seawater. It also the delta proteobacteria, they use sulfate and they produce sulfide. And in the transition zone, those sulfur oxidizer, they produce a lot sulfate, and they decrease in the seagrass area again. So let's switch to a heat map. So from the heat map, we can see all the sample dominate with the proteobacteria. And only in the white mat, they switch to a different microbial community. In the deep sample, it switched to archaea. And in the shallow sample, it switched to firmicutes and actinobacteria. So if we calculate the correlation coefficient of each phylum, we can see the archaea, they always prefer live with the other archaea. But the other aerobic bacteria phylum, they always prefer to grow with the other aerobic bacteria. The only exception is the Thammaceota. So Thammaceota, they prefer those with the cyanobacteria, firmicutes, and they always grow together. And the proteobacteria, if they show up in the sample, you cannot see any archaea in the sample. So I want to know how the cluster analysis, and this is a calculation result. So the seagrass and the background, they always cluster together, and the transition zone and the white mat. No matter I use the all community or the bacteria community to calculate it. And the next part, I use a source check to check the microorganism, how to mix with the seawater and the venting fluid. So I set up 3 different sources, like seawater, background sediment, and the venting sediment. So based on this result, like the white mat area, they definitely dominate with the vent sediment microbial community. But the backgrounds and the seagrass, it dominate with the sediment, the background sediment microbial community. But in the transition zone, they all mix with the seawater, background sediment, and the venting sediment. So the microbial community, it just mix from the seawater and the vent. So they mix with each other, and they have some unknown. And this is the next step I need to figure out. So the roughly summary of my research, the geochemistry is controlled by microbial community. Even the microbial community just mixed with the seawater and the venting fluid. But because the microbial community, they have a different metabolism in here. So they regulate the geochemical cycle in this system. It's become so different. It's not only just associated with depth and distance. So next step, I need to finish the quantify of the function gene to figure out how much, like what kind of metabolism located in each site, and run the precrust and to predict the functional profiling of a microbial community with distance, depth, temperature, pH, or even each different geochemical profile. And I will run some metagenomics analysis. My proposal just got proved by the Deep Carbon Observatory, and found that I can send the metagenomics sequencing for them. And the future work, I will combine the previous data I already finished, like the cultural and the thermodynamic calculation, and hope I can construct the whole biogeochemical cycle model in this shallow hydrothermal systems. And I need to thank for my advisor and all the limits in my lab. Okay. Thank you so much.
Okay, we have time for a few questions.
Yeah, thank you. That was a fantastic talk, and it sounds like really fun work. I'm curious if you think the reason that you're not seeing archaea in the samples with proteobacteria is solely spatially related, so that you're just not collecting samples with archaea in them because they're not in that part of the water column, or if there's an out-competition of some form that having proteos in your sample automatically means that they're doing something that the archaea then can't survive in that area. I don't know if you have an idea about that.
So actually, they still have like little bit archaea in the other column, just not too much because the temperature is much lower than the vent. So I think the most archaea survive here. They need a high temperature and a low pH environment. So that's why they switch the community.
Okay, thanks very much.
Okay, thank you, Guang Sin. Let's see here, and now, sorry.